Everybody's received the exam. So let me go over it with you very quickly. Because I know at times my handwriting leaves something to be desired. And I want to make sure that you understand what we have. Okay, we have an 8-meter beam. It's made up of 2 sections. There's beam or bar A, and I've given you specific information about it. Its length, its cross-section, various physical properties about it, including yield strengths, ultimate strengths, modulus of elasticity, modulus of rigidity. The second bar is 8 meters long, bar B, and I've given you specific physical information about that.
Professor?
Yes.
I do not want to ruin your day, but I think you resent the same exam.
Because the other one I sent was a quiz, right? Let me go back. Hang on a minute. I'll go back to my email.
Yeah, it's the same thing. I have them both opened.
Okay. And I admit. They are different. The one I sent you, at least according to this computer, I thought, showed a number that is 10 meters long, 8 meters and 2 meters, at an angle of 28 degrees with the one wire. So let me go back to my mail again. Okay, the one I just sent you should say at the top of the page, exam number 1. What? The one I sent you before said quiz number 3.
They both say exam.
Say that again?
They both say exam 1.
Professor, I think you sent us the correct exam the first time. They both said exam 1 on them.
Because the one I had pop up on the computer here in the classroom says quiz number 3. But let me go back to the. All right.
It's
Let
a
me go back.
it's a 2-wire attachment with a 40-degree angle.
Yes, that's the exam, 40-degree angle. Let me go through that one with you now and make sure everybody has the correct one. And then obviously you're not going to do quiz number 3. I set up quiz number 3 just in case you opted to do the exam on either Monday or Wednesday of next week to give you more practice. But let me go through what we have for exam 1, and hopefully everybody has the correct one. And I know I just sent it a minute ago. I'm not sure what happened to the earlier one that I did. Anyway, you have a system where there are 2 bars that are together. One is 2 meters, one is 6 meters, for a total length of 8 meters. For the first bar, bar A, I give you physical parameters about it. If length is 2 meters, cross-section is 2 centimeters by 2 centimeters. I give you the yield and ultimate plane stress, shear stress, and I give you the modulus of elasticity and rigidity.
Can I just get a
Yes?
I hate to interrupt you, but I need to get a clarification because the cross sections that are on this sheet that I'm looking at are 1 centimeter by 2 centimeters and 4 centimeters by 2 centimeters. You're saying they're 2
I'm
centimeters
sorry. No, they're 1 centimeter by 2 centimeters.
Okay.
And then 4 centimeters by 2 centimeters. And then bar B is 6 meters long, cross section is 4 by 2. And again, I'm giving you the yield and ultimate for both plane and shear stresses. And then Young's modulus and the modulus of rigidity. When you look up at the member in question, there are 3 shearing forces acting down: 10,000 newtons, 20,000 newtons, 30,000 newtons. And it is attached by a wire on the right-hand side that is at an angle of 40 degrees. It is also attached by a wire on the left, but you do not know that angle. So what I'm asking you to do is, for 100 points, is to sketch a complete free body diagram for our 8-meter bar. Complete. Then I want you to tell me what is the angle that the wire makes with the horizontal on the left-hand side. And I'll tell you, it is not 40 degrees. You're going to have to find that. And then finally, the balance of the exam, I want to know, is our system safe? And again, I strongly suggest that you do all the calculations just to make sure that you haven't inadvertently made a math error. Again, if you make a math error, I'll take off for it once, but then I won't take off for it again as long as you follow through with that. Okay? I'm sorry about the confusion. I made up both the exam over the weekend and I made the quiz this morning. And I put both of them, I scanned them into my computer. For whatever reason, it only took the quiz, not the exam. And so what I sent you earlier to start with was a quiz. So please just throw that away. I was going to let you do that as a warm-up if we had the exam next week. Any questions on the main part of the exam? This will be due Wednesday at 3:15. I want you to show all your work. And then for extra credit worth 6 points, we know the original length was 8 meters. I want to know what is the final length of our bar with the loading as shown. So it's possible to get 106 points on a 100-point exam. Any questions on that?
Professor, is the 20,000 Newton force, is that 1 meter from the 10,000 Newton force or from the end of the 6-meter beam?
It's from the end of the 6-meter beam.
Okay.
So beam A is 2 meters in total length, and the 10,000 force is 1 meter from the end. Beam B is 6 meters in length, and the 20,000 Newton force is acting 1 meter from the left end. The 30,000 Newton force is acting 1 meter from the right-hand end. Any other questions on my handwriting, what I'm after? And again, I'm sorry about that initial confusion. I'm not sure why my computer did not accept the scanned-in exam that I did this. Well, I wrote it over the weekend, but I scanned first thing this morning. And then I also, yes.
So is the exam the first one you sent or the second one you sent? The second one?
The one I sent you just now should have at the top exam number 1.
Okay, so
The other one that I sent you before, if you look at the top, it'll say quiz number 3. I made up the exam over the weekend. The first thing I did was I scanned that to myself this morning. Then I figured, just in case you decided that you'd rather do a heavier quiz and do the exam next week, I made up quiz number 3, and then I scanned that to myself later this morning. For some reason, I used the scanner at the president's office. The initial exam one did not, my computer did not take it this morning. I only had the quiz. So what I sent you was inadvertently, I sent you the quiz rather than the exam. But I just went over the exam with you. Hopefully everybody is working on the same exam.
Okay, okay, second one exam. Got it.
Second one was the quiz. I don't know why my computer did not accept the first scan, but it didn't. And then when I came down here, I saw nuclear material science, and I clicked that onto you, and as soon as I looked at it, I knew it was the quiz, which is the wrong one. If you want a little practice, you can do that. Wouldn't hurt you to do that. You don't know what Poisson's ratio is yet. I'm going to lecture on that next week.
Professor, I just wanted
Yes?
to clarify something on the diagram.
Yes,
The 30,000 Newton weight, is that 1 meter from the right side of beam B and 5 meters from the left side of beam B?
correct.
All right, thank you.
Anything else? Okay. Again, I designed this so that if you were here on Wednesday, I would have given you this, gone over it with you, and then you would have had till the end of the class to do it in class and turn it in. And I figured some extra time in there. Basically what I do whenever I make up a quiz or exam, I use a factor of 3 to 1. So when I make it up, I take it, and then I will typically give you 3 times that to do it, whether it's a quiz or an exam. So you should have plenty of time to do this, even if you started on it on Wednesday at 12:30. I'm giving it to you now so you do have that extra time. I will be around tonight till about 6 if you need to get hold of me on anything. But then I'm leaving early tomorrow for Denver, and I won't be back till Saturday. Okay. Has everybody hopefully been taking a little break here so I'd like to lecture a little bit now on reactor theory before we call it a day. Okay. And again, I'm planning to have the exam for reactor theory next week. I will probably do it on Wednesday in class. Excuse me. We're going to make that the following Monday because I'm going to be involved with the accreditation for Missouri State University on that Monday. And I'll be bopping in and out, so I'll give you the exam on that Monday to do in class. You'll have the entire time from 12:30 to 3:15. I will be bopping in and out because I'll be conducting Zoom interviews with the president, the dean, alumni, industrial advisory committee members, faculty, students, etc. But I should be able to get away for 15 minutes to get you started. Make sure you understand what I want on the exam. And it'll be due at 3:15 on that Monday. Okay. If we go
That's
back
Monday.
that
That's
is
Monday the
Monday.
27th.
That is, today is the 20th, so it'll be 2 weeks from today. We'll have reactor theory exam number 1 in class. Okay. We've gone through natural decay. And we've looked at natural decay with alpha, neutron, proton, electron, positron, and electron capture. We've looked at multiple decay, multiple natural decay, and this is where you create more than one decay product. In the quiz, we've also looked at induced decay, and what I'd like to do now is, if anybody would like to put up or present reactor theory quiz that was due today, if anybody would like to put up that, we can go through that. Or if you don't want to put it up again for extra credit, I will put my solution up. Would anybody like to put theirs up? Okay. Okay, I told you had an atom of bismuth. Get this to write a little darker. I told you we're going to strike it with an alpha particle. And I asked you to create a reaction equation that produced one neutron, one electron, two protons. And I choose to write these out. You could have written two, but when you do that, sometimes you forget that you also have a difference in number for subscript and superscript. In order to have that, you always include the possibility of gammas plus kinetic energy, plus we know we're going to have something else, plus, because we have an electron, we know we have to have an anti-neutrino. So when we look at this, we know that the subscripts have to match. So 83 and 2 are 85. On this side, this cancels with this, so we have 1 plus whatever the question mark is, so the question mark has to be 84. If we look at the superscripts, that's going to be 209 plus 4, which is 213. If we look on this side, we have 1, 2, 3 plus something. So that something has to be, make that equal 210. So using the subscript to identify the element, we know that that is.
How did you get 84 for the subscript?
On the left-hand side for these subscripts, we had 83 and 2, which is 85.
Yep.
If we look on this side, we have -1 and 1, so they cancel one another out. So we have 1, and then whatever has to go with this guy, 1 plus something. So the 1 plus something has to equal 85. So that has to be 84. You with me?
No.
Okay.
If you do 85 on the left-hand
Yep.
side, you're subtracting the electron, which is -1. So that's 84.
We're not subtracting the electrons on this side. We're just doing.
No, I understand, but you have 85. Then you subtract the 1 electron, which would make it 84. And you have 2 protons, which is 1 plus 1. So how would that be 84? Wouldn't it be 86?
If we look at the subscripts on this side, The only subscripts we have are -1 and 1, which cancel each other out. So we have 1 plus whatever has to be here. So on this side, we had 83 plus 2 for 85. On this side, we have -1 and 1 that cancel each other out. So we have 1 plus something. So that something has to be 84. So that 85 equals 85 for the subscript.
Okay.
Then we did the same thing for the superscripts. 209 plus 4 is 213. Over here we have 1, 2, 3, plus whatever this is. This has to be 210 equal that. So this is our complete reaction equation. I then have asked you to find out if it could occur. So we can look at the mass and energy on the left minus the mass and energy on the right. So I have the mass of the bismuth minus 83 mass electrons plus, and alpha is the mass of the helium minus 2 mass electrons. Now we come on this side because we don't have anything else on the left. So you have minus the mass of the neutron, minus the mass of an electron, minus the mass of a proton, minus the mass of a proton, minus the mass of polonium, minus 85 mass electrons. That's equal to Q. Collect like terms. So I have mass of bismuth plus mass of helium minus mass neutron minus, and I still kept these as separate, mass proton minus mass proton. Yes, you could have wrote 2 mass proton if that makes you feel better. Okay. Minus the mass of the polonium. Now we have to count electrons. So we have minus 83, minus 2 is minus 85, minus another one is minus 86. And down here we have minus a minus, which is plus.
It's supposed to be
85.
polonium 84, Professor, not 85.
Oh, thank you. Had it here, right? So we have a net of minus 2 mass electrons. So if I then throw in the values for this, I have for this 208.9804 plus 4.0026 minus 1.008665 minus, I'll go ahead and do the 2 times 1.007665 minus 209.9829 minus 2 mass electrons, which is 5.4858 times 10 to the minus 4. When I did that algebra, the value I came up with was minus 0.0242 AMUs.
Professor, can I ask a question?
Sure.
So why do you not count the 2 mass electrons for the protons? Like, why do you not add that in there? Because you add the mass electrons in for the bismuth and the helium.
Because we already have mass values for the neutron, which is the 1.008556, that's 5 rather, and for the proton, which is the 1.007665. We already have the mass for that. We don't need to do any adjustments.
Okay, so up when you're doing the M plus E equation, you don't include the mass electrons for the protons or the neutrons or anything like that?
for example, we know what the electron mass is. If it was a positron, we know that that's the same mass as an electron. If it was an alpha on this other side, we know how to account for that. So anything that you're given a value for, and we know it for neutrons, electrons, positrons, protons, and alpha, you don't need to do, like, try to break this down into other.
So then for the alpha in the Q equation, why do you subtract the 2 mass electrons after the mass of the helium?
Because we're doing nuclear mass balances, not atomic mass balances. So when you go in the back of the book and you find this value, that is the atomic mass balance. That includes the entire atom, which includes all your nucleons plus the electrons. Everything we're doing is a nuclear mass balance. So when you do that, you have to account for the electrons.
Okay.
So for the missing nuclide, we have to figure out so are we always going to assume that it's neutral, or would that not always be the case?
You mean when we start off up here? When I write the reaction equation, I would typically recommend that you assume that anything on the left-hand side, unless I tell you otherwise, does not have any type of kinetic energy. So you're going to look to see if these two were basically stationary and just brought together, could this occur? And from doing our reaction equation, then doing our Q equation, and again, you might get a slightly different number depending upon how much you rounded off these various mass values. This is the value I got. The negative tells you it cannot occur unless you add energy, and if you multiply this by 931.15 MeVs per atomic mass unit, cancel, cancel. I had that value come out to be kinetic energy had to be 22.52 MeVs, which is this times this. So my alpha particle has to have at least that or greater in order for this to produce those particles.
Okay.
Everybody with me on that? So the key is writing out the correct reaction equation, and then writing out the Q equation, and then substituting in, collecting like values.
Professor, when you were writing out the mass of the individual components, at the end you wrote -2, and then there's a number following it in parentheses.
This is
Where
the math.
where did that come from?
That's the mass. There's two electrons that we have to account for. So this is -2 times the mass of an electron. So I have 2 times, and this is the mass of an electron in AMUs. And again, it goes back to summing up what we had written down for our Q equation. Again, -83, -2 is -85, -1 is -86, and then we had 84 for this, so it's a net of -2 electrons. We do have to account for those. Do you understand that, or? Say that again. Okay. Okay. Have you followed my logic through the Q equation? Let me go back and I'll go back and rewrite the Q equation. I'm going to erase all this. Okay, hopefully you agree with me that this is the reaction equation. This is the equation for Q, and now I'm going to go and write out Q. So I want the mass and energy on the left. So I have my bismuth. It has 83 electrons. So I have to subtract 83 mass of electrons from the mass of the bismuth to come up with the nuclear mass balance. And then on this side I have plus the alpha, but we know the alpha is the mass of the helium minus 2 mass electrons. We've counted now for everything on the left. We have to account for what's on the right. So we have minus the mass of a neutron, minus the mass of an electron, minus the mass of a proton, minus the mass of a proton, minus the mass of polonium, minus its electrons, which were 84 mass electrons. So I go back and combine like terms. Mass of bismuth plus mass helium minus the mass of our neutron. I'll just keep those separate now. Mass of proton, minus the mass of my polonium. Now I'm going to account for electrons. So I have minus 83, minus 2, minus 1, minus times minus is a plus 84. So minus 83, minus 2, minus 7 is minus 86, plus 84. So that tells me this is minus 2 mass electrons. Then I go in and I throw in the values for all these, for my masses, and I come up with a value. If the value is plus, this can occur. If the value is negative, it cannot occur unless you add energy to the left-hand side. And you could have done that a number of ways. In this particular case, I asked you, what would the energy of the alpha particle have to be? We looked at that mass difference. It was negative. We multiplied that by the 931.15 MeV per AMUs, and we came up with this amount of energy is the minimum required for the alpha to have in order for this reaction equation to occur. Everybody with me? Anybody not with me? Okay. And then for the extra credit, we know kinetic energy is equal to 1/2 mass times velocity. We know the kinetic energy. We know the mass, and what mass are we going to use?
Helium.
That's right. So it's going to be 1/2 the mass of our helium, which is 4.0026 AMUs. And we're out for velocity. So we have one equation, one unknown. We have to get AMUs and MEVs into units that will give us a velocity in meters per second. So basically, you're converting this energy into joules, and you're converting this mass into kilograms. And the answer I came up with was, the velocity was 3.26 times 10 to the 7th meters per second, and this is the velocity of my alpha particle. Again, that was strictly extra credit. Do you feel you understand, because obviously you're going to get this on the exam, do you understand how to write reaction equations and then calculate Q? If not, we could just make up one and do one now for practice. Let's make one up. Okay. I'm just going to go to the chart of nuclides. Anybody want to throw an isotope out at me that we'll start with? Just pick one. How about
68 ER? I don't know what ER mean though.
$58 is CE for.
I said 68. 68.
Oh, 68.
ER 172.
That is erbium. Okay. Okay. You want to pick a particular isotope? What do you want for the superscript?
172.
I'm sorry, I can't hear you.
172.
172. Okay. Okay. Let's say we strike this with a proton. And I ask you, can this create an electron, a positron, plus an alpha particle? So the first thing you need, so can I strike my iridium 172 with a proton and create an electron, positron, and an alpha particle? So the first thing you have to do is write the reaction equation. So we know we're going to have something, and I'm just going to extend it down here, plus we always account for gamma rays plus kinetic energy. And in this case, since we have an electron, we know we have to have an antineutrino. Because we have a positron, we have to have a neutrino. We then need to find out what is this unknown thing. And to do that, we're going to match subscripts and superscripts. So on the left-hand side, if I look at subscripts, I have 68 plus 1 is 69. If I look on the other side, I have minus 1 and plus 1, so they cancel one another out. So that's going to be 2 plus whatever that isotope is contributing. So this has to be 67 in order for this total to be 69 to match this 69.
Can I ask just a question about this? Should you or do you need to include what the compound nucleus is in between the two steps?
We're going to pick that up in the next chapter. I certainly would encourage you to do that. And if you did that, rather than draw this, you would have this is going to be our compound nucleus. know the compound nucleus is going to be 69. The top is going to be 173. So whatever that guy is, which is TM, which is thulium, and I don't know how Professor Abel might have taught you how to do compound nucleuses. What I'd like for you to do is always put a little asterisk there. The reason we put the asterisk is we don't know how the energy is distributed within the nucleus itself, or it could be in the electrons surrounding it. We don't know what that is yet, but you put this step, then you'd come down to the rest of this. That's the way I'm going to get you to write everything starting with the next chapter when we do compound nucleuses. But we'll just leave this.
Okay, thank you. And I just have one question, maybe a stupid question about the electrons, but so that yields an electron and a positron. Are the signs in front of the ones just denoting their charge, not whether they exist or not? So how do they cancel each other?
This is denoting that it's, by seeing the minus, you know it's an electron. By seeing the minus, you know it's a positron.
Right, no, I understand that, but then you use that to cancel each of them in the last equation, so I'm not following the difference.
It's just the way that you account for various particles. This is the way you account for an electron, this is the way you account for a positron, just like this is the way you account for an alpha particle, or this would be a neutron. But you have to account for these subscripts whenever you're coming up with the subscript for whatever this isotope is going to be, just like you have to do this superscripts to come up with the superscript for the isotope of interest. Now, why did they come up with this terminology to start with? I honestly don't know, but they did. So in this particular case, we said that subscripts were 68 plus 1, or 69. Then on this side, this cancels, so that had to equal 2 plus this. So this had to be 67. And then for the superscripts, we had 172 plus 1 has to equal 4 plus question mark. So 173 has to equal, this would be 169. So again, we said that that was HO, which is helium. So this is this particular isotope of helium. This is our complete reaction equation. So to see if it can happen, we have to go back and do a Q calculation. So that's going to be the mass and energy on the left minus the mass and energy on the right. So on the left, we have the mass of ER minus 68 mass electrons, plus the mass of a proton, minus the mass of an electron, minus the mass of an electron, because the mass of an electron and a positron are the same, minus the mass of helium, minus 2 mass electrons to make sure that's a nuclear mass balance, minus the mass of our helium, minus 67 mass electrons. So we've written the reaction equation. We've now spelled out the Q equation. We combine like terms. So we have the mass of ER plus the mass of a proton minus the mass of helium minus the mass of a helium. Now we have to look at electrons. So on this side we have minus 68. On this side we have minus 1, plus 2, plus 67. So minus 68, minus 1 would be minus 70. Plus 2, plus 67 would be plus 69. So it tells us we have a net loss of 1 electron. Everybody follow?
I got a question.
Yep.
So the mass of electrons canceled out this time?
No.
No, it's just okay.
This is a mass of electron. This is a mass of electron, and we've included this to show, or maybe I didn't show. Let's see. 68 minus 1 plus 2 plus 67. So I put everything in. Let me erase this again. So when I wrote out my Q equation in full, I then go back and collect like terms, and I always do everything except the electrons first. So I have mass of my ER plus the mass of the proton minus the mass of the helium minus the mass of the helium. Now I'm going to go back and account for all the electrons. So on this side I have minus 68 minus 1 minus minus is plus 2, minus and minus is plus 67. So I have minus 70 plus 69. So that tells me I have 1 electron I have to count for. So I put it in here. I would then go back and substitute in all the values. This is a mass of the ER nucleus. Mass of a proton is 1.007276. Mass of the helium is 4.0026. The mass of helium is whatever the mass of that nucleus is. The mass of electron, there's one of them, so it'd be the 5.4858 times 10 to the minus 4. You sum all of this up, and again, if it's negative, it cannot occur.
Can we do that now?
Okay? Let's do that now. Okay. So the mass of...
I can tell you the mass of the ER. It's 171.
Okay, 171, and what's the rest of it?
0.939361.
9393, okay. Plus the mass of a proton, which is 1.007276, minus the mass of the helium, which is 4.0026. Let's see if they have the helium in what I'm looking at here. And they don't, so you might have to look at that either in the back of the book or probably on the internet.
I'll look it up for you.
Okay.
All right, for that it's 168.936878.
Okay. And then minus the mass of an electron. So I'm just going to write that out, 0.00058848. Okay. Then if you got a calculator, we're going to do this algebra, add this and this together, subtract this, this, and this, and I'm going to come up with a value. So let me know what that value is.
What was the mass of the electron again?
5.4858. 5.4858. Let me go back to the book, just make sure I'm giving you that correct. Mass of an electron is 5.4858 times 10 to the minus 4. So this should be 5.4858. So if you do this algebra, I'll see if I can do this at the same time with you. Let me know what you got.
I got 0.0061042.
Positive?
Yes.
Okay. So I got okay. Zero point zero zero 663 AMUs. It is positive. So this can occur because this is positive. And if you multiply this times 931.15, it would be, and you cancel. I get 6.17 MeVs plus. So that tells me this can occur. And when it does, you will have this much energy left over to distribute on the right-hand side. And that typically is going to be in the form of either kinetic energy for the alpha, kinetic energy for the helium, and or one or more possible gamma rays. Remember, when we write this equation, all we can tell is that it does occur and that this much energy is left for the right-hand side. We do not know how it's distributed. It could turn out that this is one gamma ray of this amount. It could be two gamma rays, one of 3.17, one of 3. It could have part of the energy here, kinetic energy, part of the energy here, with no gamma rays. We don't know that. There are other things you could do to determine that. If you had a cloud chamber and you ran this, you could identify particles in the cloud chamber and measure their velocities and relate that back to kinetic energies. We don't have any of that instrumentation here at the college. Does everybody feel comfortable working these? Okay. Because you are going to get, should I say, multiple of these on the exam. I haven't made up the exam yet, but I'm going to look to see natural decay and induced decay. Any questions on that? Okay. Before I forget it, before I leave today, I will grade the 2 quizzes that were due today, and I'll leave them back in the box just in case you want to use them for, or at least the one of them for the exam that you have. If there's nothing else on this, I would like to start one new topic for about maybe 10, 15 minutes, and then we'll go from there. Any questions again back on this? All right. Let's say I have a radioactive isotope. Let's call this A. And let's say it wants to decay electron. I'm sorry? Question? So we have a radioisotope A. You were saying when it decays, it produces B. It has a half-life. Let's say B is also radioactive. And it decays, let's say also by electron, to C, where C is a stable isotope. Let's say this has its own unique half-life. If I started out with a certain number of atoms of A, let's say I had 8 times 10 to the 18th atoms at time equal to 0 for A, and I run time, can I look to see what's happening with the buildup and the loss of A, B, and C? And the answer is yes. Let's say this half-life is 30 days. Let's say this half-life is 20 hours. What is going to happen? A is going to decay, and how is it going to decay? It's going to decay via the regular decay scheme. We know that the number of A's being radioactive is a function of time. It depends on the number of A's that you had to start with times its decay constant as a function of time. If I plotted that, where this is time and this is number of atoms, we know that time is equal to 0. We start off with this number of atoms. It is then going to decay according to its decay constant. In its decay, it's going to look something like this. This curve is the plot of that equation. So we have one equation with two unknowns. The unknowns are number of atoms of A at any time. Time is the independent variable. Number of atoms of A is the dependent variable. So if you tell me the time, I'll tell you how many atoms of A you have remaining at that particular time. Nothing new or magical there. We've done that in the past, hopefully in Professor Flory's and Professor Abel's classes. And we did it to start this time. What about B? Can we determine how many B's we have at any particular time? And whenever you're looking to try to identify something along this line, we typically look at a rate of change with respect to time. So if we look at the rate of change of B, with respect to time, we can always say, whenever we write this type of equation, that it is always production minus loss. So this is looking at the rate of change with B with respect to time. So if we look at the production, where does the production come from?
I don't have got the answer for production, but what does it say after production? Is that 1055?
Minus loss.
Oh, loss. Okay.
Okay. So where do the B's come from? They come from the radioactive decay of A. So if we make this production as a function of time, if we look at the rate of change of the number of A's with respect to time, we're going to differentiate this equation. So if we differentiate this, this is going to be NA0 and then minus lambda A e to the minus lambda AT. You've done this before in your calculus, I hope. Okay. So what do we have here? The rate of change of A is minus lambda A NA0 e to the minus lambda AT. That is a rate of change of A with respect to time. That is also the production of B. So the loss of A's is the production of B. So I can put this in here. And I would change the sign because this is telling you that the A's are decaying. This is telling you that you have a production which is plus. Okay. What do we have for the loss of B's? And if you want to follow this in the book, you could follow on page 59. But the loss is solely the decay of B's with respect to time. And this decay, we could say it's minus because it's decay, and it's going to be the decay constant of B times the number of B's that you have at any particular time. So we could then substitute that back into this loss. So we have the rate of change of B with respect to time, which we know is production minus loss. We then substitute in what that is. That is lambda A NA0 e to the minus lambda AT minus lambda B in V of T. So we have one equation, two unknowns, NB and T. We can solve that equation. If we do, and hopefully you could do this from your algebra, the answer for this comes out to be number of B's with respect to time is equal to, and you can follow the math on page 59 and 60. It's going to be lambda A times NA0 divided by lambda B minus lambda A. All of this times e to the minus lambda AT minus e to the minus lambda BT. So I have an equation for B as a function of time. This is the equation that does that. And all I've done is solve this. And if I plot that, what would that look like? If time is equal to 0, how many B's do I have?
Zero B's.
You have 0. Because at time equal to 0, all of them are A's. And then as time goes on, you have this production minus loss. And if you plot this, the plot of this equation with time is going to look something like that. It starts off at t is equal to 0. And then we go out here towards infinity. How many B's do we have? We have none, because they have all decayed to C's.
Okay. Wait, do we like as of right now, do we have all the numbers to be able to insert into that equation or not?
Yes.
Are we gonna have to do this for this quiz, or it's just
Not for right now. I'm going to go over it next week. I'll
okay?
give you a take-home quiz, and it'll probably be on the exam for Reactor Theory quiz, exam number 1. But we'll work one of these problems before then. Okay? So, this is the plot of B with respect to time, which is this equation. Okay? You then might say, what's going to happen to C's? So if I go back and look at C's, okay, C's only created from B's. So we could go and look at what is the rate of change of C, or in sub C, with respect to time. And it's going to have to do with the rate of change of production minus loss, because that's how you define the number that you have. Where does the production come from? It only comes from B's. So we'd have to go back to this equation. If we differentiate this with respect to time, that would be the production. It would be plus because we're creating them. How about loss? What do we have for losses? We don't have any losses because C is stable. It's not going to decay. So we could solve this to find C as a function of time, but there's a much easier way to do that. And to do that, when we start off, we know that the initial number of atoms is equal to, at any time, the number of A's plus the number of B's plus the number of C's. So if we look at what's happening to C's, how many C's do we have at time equal to 0? We have none, because everything is an A. As time increases, the C's will also increase, so that when we go out towards infinity, that plot is going to look like this, where this is N of C with respect to time. At time equals infinity, all of the A's will have become B's, all of the B's will have become C's. So at time is equal to infinity, the number of C's at infinity will be exactly the number of A's that you started with. So if you wanted to find the C's at any time, you draw a straight line here, we could go back and say this number is equal to the number of, let's say we pick this time right here. This is the number of A's. That's the number of B's. So if we have this minus this and this, we will have this. So that any point in time, if I add, let's say I pick a point right here. If I add the number of A's at that point, add that to the number of B's at that point, and I add that to the number of C's at that point. If I add this, this, and this, I will always get that constant number because we're not changing the total number of atoms. Okay. I'm going to pick up on that on Monday in class. If any of you think you have followed that and you want to try to do an extra credit problem that would be due on Monday, if you look in your textbook on page 65 and problem number 14, it talks about Ca47 decaying to Sc47 and ultimately going to titanium 47, which is stable. And it asks you how long would it take for the Sc to reach a maximum, and what are the relative amounts of each one at that time. If you want to try to work that problem, turn it in on Monday. I will consider that extra credit. The nice thing about this is the even numbered problems, the answers are in the back of the book. So if you do try to work it, you'll at least know if you're getting it right. So if you try to do that, that's extra credit due on Monday. Again, I'll be around today till 6. I'll leave your 2 graded exams in the box before I leave tonight. Good luck on the exam. Just make sure you show me everything that you're doing, because again, I give partial credit. I don't think it's that difficult because I set it up so you can do it within our regular class period. You can wait till Wednesday to do it. I'd probably encourage you to spend a little time an hour ahead of time, just so you'll do well on it. Any questions on anything? Okay. Good luck on the exam, and I'll see you next time. Yes.
On the extra credit, you said page 85?
65.
65.
So it's it's problem number 14 at the end of chapter 3.
Okay, yeah, that makes more sense.
So if you try to do that, hopefully you can get it right, because it is answers in the back of the book. Even if you don't get it right, submit it and I'll correct it accordingly and give you a little bit of extra credit. Okay. Good luck on the exam, and I'll see you on Wednesday.
Professor, what was the